जब शुरू करना है मेरे को बता देना ना। एक मिनट बात। Hello and welcome to the last lecture of Advanced Material Chemistry course. This HBNI. In this lecture, we will see crystal growth and other techniques. In last lectures, we saw thermoelectric effects. Seebeck effect, Peltier effect, and Thomson effect are these important thermoelectric effects. We saw each of them. And thermoelectric figure of merit is defined as alpha square sigma divided by K into T, and it is written as ZT. Actually, if you remove this, it is Z, but ZT is T is deliberately multiplied to make it dimensionless. Then we discuss transport properties and heat conduction. Then method of improving ZT values by impurity adding, nanostructuring of thermoelectric materials, etc. Then we saw some of the important thermoelectric materials. Then thermoelectric devices also we saw. Then towards the end, we learned some important elemental and compound semiconductors, like the properties of these materials, germanium, silicon, and some compound semiconductors, amorphous silicon also. Today, what we are going to learn is single crystal growth and growth techniques. Some of the techniques like Czechoslovsky, float zone, hydrothermal. And then we will also see how the crystals of silicon and gallium arsenides are grown, and then how to make wafers out of these crystals. And another important crystal is quartz. We will see how the crystals of quartz are grown. Then we will also see different thin film deposition techniques, which are thermal, electron gun evaporation, DCRF sputtering, epitaxial film deposition techniques, CVD, and all of this kind of and a brief introduction of 2D and 3D printing, because syllabus is large, so we will try to go as quickly as possible in this lecture, so we'll go the fast. So first, let us see crystal growth. We saw that crystals are required in order to make devices or in order to make semiconductor. So first, let us see what way these materials differs from other phases. If we start, like, you have atoms, but these atoms are having very high energy. In fact, very high energy, and they are when they have very high energy, they remains in gaseous state or vapor state. So if we consider the vapor state, we can see the atoms, molecules have very high energies, and as from the basics, we know that 1 mole of the gas, it occupies 22.4 liter of volume. So, and they are very far from each other, and the interaction is minimum. And if we see the distance between two atoms, typically more than 30 to 40 angstrom, and even more. It depends on how dilute they are. And they are, because they have very high energy, so they are actually in continuous motion, and just because of this energy. Now, if we try to remove this heat from this energy, whatever energy is with those, so this energy is in the form of, we can say, their kinetic energy, or so this heat, if we try to remove, what will happen? They will slowly try to, you can say, try to be a little vigorous. The kinetic energy will reduce, will try to come close to each other. So then in that case, they condense in the form of a liquid. So if we come into liquid, these have relatively less energy, uh, less volume, occupies less volume as compared to gas. Distance is also less as compared to gas. And then the motion is also, it is not like in gaseous state they were going everywhere. So now they are confined to the volume in which they have been liquefied. I'm talking about the same material or same atoms which were in gaseous state and now they have become in the liquid state. They are not two different kind of atoms. So it will be, it should be kept in the mind. Now, if I further reduce energy from this, then what will happen? They will achieve a lowest energy, and they solidify and they become solid. So what is the property of solids? They have the lowest possible energy. The distance between two atoms is now of the order of angstroms. They ideally they do not move, but if they move, they have very little vibrational motion around their mean position in the solid, and so we can call them as a densely packed atoms when we speak about the solid state. And these atoms interact with each other very intensely. So we have same, if we go in a reverse way, suppose I start heating a solid, the energy of these atoms will start increasing, and after a certain level they will achieve so much energy that they will go into a liquid state. And if you further start giving heat to this liquid, it will vaporize. Now, you see these two boundaries, when a liquid converts condensed into solid, or a solid uh, converts into liquid. So this is a phase transformation, and every phase transformation and these are first order phase transitions. So every first order phase transitions have a latent heat. So latent heat is associated to these every first order phase transformation. So what is that heat? So when actually solid is converting into liquid, the constant at constant temperature, the temperature will remain constant, but you need to supply additional heat which is equal to the latent heat of this transformation. That is called as the heat of fusion also in some cases. When they are coming from liquid to solid, the heat is same. So just remember, whenever there is a phase change, in that case, always a latent heat is involved. So when some liquid is being converted into solid, a certain amount of heat is going to be liberated. Now that heat, where that heat will be liberated, that heat will be liberated at the interface. Now it is extremely important to extract that heat out from that interface. So therefore, the material which is crystallizing or which is solidifying, if it is having a good thermal conductivity, the heat can be easily swept away from the interface, and it can be, you can say, transferred to the system. Therefore, the crystallization of metals is very, very easy. You can have very fast crystallization, but some materials which are actually having a very, very low thermal conductivity, it is very, very difficult to make a crystal out of them. Usually, because the heat from the interface, whatever is being liberated, it cannot be passed to the surrounding. It remains there, and so the atoms which were supposed to have minimum energy when they want to go at the perfect lattice sites, they already have a lot of energy, and before they release that extra energy, they become fixed, and therefore they go into amorphous phase. So therefore, it is very difficult to grow crystals of oxide materials which have poor thermal conductivity as compared to the metals. Metals, because of good conductivity, they always crystallize, and the best possible, the closest possible structure, that is face-centered FCC structure. Closest is the FCC. We saw that. So that is so you can see most of the metals they crystallize in the FCC structure. So this is just an idea how a solid is formed. So now this solid can, suppose these are crystals. So or the atoms have become now not crystals. The atoms have become now fixed. They are not moving. So the solid can be of three kinds on the basis of structure. They are amorphous solid, where you can see there is no periodicity. You have one atom and you have another atom here, but if you go in the same direction, you will not find the third atom the same. So there is absolutely no periodicity. Every atom has a different surrounding, and there is no rule how it will crystallize. However, in polycrystalline materials, the material, say there is a periodicity across each grain. So you are having a different grains, and then there is a periodicity. So up to this point, you can say, you can call it as a crystal. Here also, this is also you can call a crystal, but then there is no periodicity here. So these are called as the boundaries, grain boundaries. So this, like whatever is there, a crystal kind of you can say volume, that is crystal part, and the where the another crystal joins this, that is the grain boundary. So however, it is periodic across each grain. So suppose there's small grain and then there's another grain, it is a periodic. However, if you come to a single crystal, so single crystal is periodic across whole volume. Means suppose you have a 1 meter crystal and you call it a single crystal, then you should be assured that entire crystal is means, and throughout the crystal there is a periodicity is maintained. So the difference between polycrystalline, single crystal, and amorphous should be clear. Amorphous means atoms have, though it's like a liquid state only, but it has become solidified. Only thing that atoms are now not mobile, but the structure is similar to the liquid. When I'm saying atoms, it can be atom, it can be, you can say a molecule also. Suppose I say NaCl, that means each of this sphere will be an NaCl. You just replace each sphere with the NaCl. So, just to see again this, what is single crystal? So, grain boundaries free monocrystalline solids that has atomic periodicity over the entire solids are referred as single crystals. They are very useful. The single crystals are only used in the devices or semiconductor devices, mostly. A polycrystalline solid or polycrystal is made up of many small single crystals. Suppose you have a single crystal and you crush it, then also whatever mass you get polycrystalline mass. The individual component crystallites are often referred to as grains, as I already said, and the junction between these grains are known as grain boundaries. the properties of a polycrystal are notably different from those of a single crystal. Single crystals form only in special conditions. You need to have put lot of efforts in order to make a single crystals. These are very difficult. However, the materials, as I already said, if they have good thermal conductivity, it is very easy to grow also a crystal, because if you have copper, you cannot make a glass of copper. It's very, very difficult to make a glass of copper. Whenever you melt it and you solidify it, it will always be in the form of single crystals. So importance of single crystals, monocrystals, single crystals show unique properties, particularly mechanical, optical and electrical over polycrystalline form. The optical and electrical properties can be anisotropic depending on the type of crystallographic structure. See, if it is cubic, then you can say all the directions are same, so the property will be same. But cubic is only one class. There are 6 other classes. So in other classes, the parameters, lattice parameters like ABC, they are different. So if there are some properties which are actually this dependent on these things. So if some property is dependent on your lattice parameters and these are varying, these are different in different directions, of course, obviously those properties will be different in different directions. So such things, such properties are called anisotropic properties, and these obviously depends upon which type of crystallographic structures are there for those crystals. Single crystals offer better radiation hardness over polycrystalline forms, and single crystals are very important for fabrication of devices like silicon chips, solid state lasers, and this beta BBO, barium borate, for doubling and tripling the frequency of laser light. So incident light is of suppose some frequency, the output light will be of double the frequency. The famous is when you have 1064 input laser and you get green light output. Using using these crystals only, non-linear crystals. Then you have quartz crystal oscillators in all the precise, you can say, watches. Wherever quartz is written, you must understand that a quartz crystal is used in these clocks in order to precisely, or you can say, measure the time. Or not only measure, precisely generate a pulse of a very high accuracy, and then there are some then you can say counters by which you can get it to up to 1 second, and then connect it to your second needle, and after every pulse your watch moves 1 second. So these are the quartz. Wherever you see quartz written on any you can say watch, you understand the quartz crystal is used there, quartz crystal was used there to control the time. More than 60% of the gold crystals are used in the semiconductor industry. So you can understand the importance of single crystals in semiconductor industry, and you know very well that most of the devices are made of the semiconductors. So crystals are therefore very, very useful. Now, how the crystals are formed? First is if you start cooling, as we saw in the earlier slide, suppose you start removing the heat. And one thing you must understand that melting point are very, very precise. If the pressure is held constant and other things are constant, melting point is very, very precise. So suppose the melting point of if a particular material is 1000, then if I start cooling that from 1100 degrees centigrade and bring it 1000 degrees centigrade, will it crystallize immediately at 1000 degree centigrade? No, it will not be crystallized. So why it will not be crystallized? Because it does not set immediately See, suppose you have a phase diagram. As I said, suppose the melting point is 1000 degrees centigrade, and it comes at 1000 degrees centigrade. It immediately it cannot become solidified. It can go even up to 950 degrees centigrade. Though the melting point is precise 1000 degrees centigrade. Melting point has not changed, but it has come down to 50 degree lower. It needs certain nucleation in order to start the growth. So for this, you need, first thing is you need certain amount of supercooling. Supercooling means the temperature difference, or you can say the temperature which has been below the melting point. So suppose if I brought from 1000 degree to 990, in that case, I can say there is a 10 degree centigrade supercooling. But once a nucleation is formed and crystal starts growing, in that case, the melting point, it will again, the growth will take place only at the melting point in that case. So change in free energy, so certain supersaturation or supercooling is necessary for spontaneous nucleation. And nucleation means a stable nucleus has to be formed. I will show it in the next slide, how the nucleation is formed. Then change in the free energy. What is the, you can say, why this nucleus is formed, and why even if suppose something is at exactly melting point, but it doesn't solidify. Suppose I have a material which is exactly at melting point, but now what will have happened? It will you have different atoms, or you consider spheres. They are trying to come together or try to make a bond and then try to grow together. So there are two kind of energies. One is associated with the you can say the surface of the entity or the cluster, and another is related to the volume. So volume energy is, suppose you have, like I will just explain. Suppose you have any atom, silicon. It is having 4 electrons, so 4 bonds are there unsaturated. If another atom comes close to it, at least one bond has been, now this is bond is made, but now if you see 1, 2, 3, 4, 5, 6 are still unsaturated. So as the volume will try to grow, this energy, this is actually this you can say where there is no bond. These you can say these are positive energies, and these bonds are at the surface. So these positive bonds, you can say these positive, you can say this positive energy is contributing, means if you if you do not, means if you try to you can say this positive energy will actually help it, so that another silicon atom can come and join there in order to reduce. This will be the negative. So now there are two energies. One is the volume energy, another is the surface energy. So volume energy is corresponding to the R cube, and the surface energy is, the surface area of a sphere is, suppose let us consider a sphere only. The surface energy of a sphere is 4 pi r square. So if we see, when the size is increasing of this cluster, in that case this is the positive energy which is increasing this side, and this is negative energy which is R cube. So below this, now the total energy will be this plus this. If you add, you will get a curve like this. So you can see up to this point, if you try to increase the size, in that case the energy is increasing. So that is not a favorable condition. All the you can say reactions where the energy actually reduces are most favored. So after that, after this point, if you have attained this radius, after that, the when you increase the size, or when the size of the cluster is increased, in that case the energy will reduce, and therefore this is a favorable state. So this radiation is called as the critical radiation. So this is a kind of homogeneous nucleation where the atoms try to come together, they try to increase the size, but if the size is below this critical radius, it is not favorable to increase the size, though 2 or 3 atoms will come together, but then they will again fall apart and it will not grow further. But by any chance, suppose you have uh, got a cluster of solid which is having a size of this, in that case the further addition of the atoms is favorable. So that size, you can say, if some cluster has been grown above the this critical radius, that is called as the nucleus, stable nucleus. And this process is called as the nucleation. And it is called homogeneous because this cluster is growing inside or increasing inside the same material. If the material is same and this you can say cluster is also of the same size which is increasing, or now we can call it a nucleus. If the nucleus is of the same material which is ready to crystallize, in that case it is called as homogeneous nucleation. Then there is another kind of heterogeneous nucleation. Heterogeneous nucleation means where you don't need this kind of condition where some solid is already there. So those can be foreign particles, that can be dust also, that could be the container wall also, because that is also solid, or some kind of substrate also where it will crystallize. In some cases you can use seed also. Suppose there is melt of something and you have a crystal of the same material, you just touch it. In that case you don't need to wait for a homogeneous nucleation or for going for a supercooling, and then you can get immediately the crystallization or growth start immediately. So now we have 2 steps. One is formation of absorption layer and formation of a critical nucleus, and then its growth. So first, a stable nucleus has to be formed. Stable means if the further size increases, in that case free energy should be reduced. Then growth takes place on that nucleus by extending it in all 3 directions. Suppose a nucleus is now has been formed, then atoms will come and these will move, and these will actually set themselves at the minimum energy positions, and the crystal will start growing. Now, what are different methods of growing crystals? Single crystals can be grown by all 3 methods: solution, vapor, and melt. Solids also it is possible, but that's called recrystallization. We will not go here for the solids. So, when you are growing from the solution, so it is normally homogeneous solution, and it gives you solid crystal for solvent. Suppose you have a suppose you have sodium chloride, like our salt, which you keep on adding inside water, pure water, and then after that you leave it like that. Then you see after many days, when the water evaporates, you can see the small crystals. So you have a homogeneous solution, and out of that you get solid crystals, and then the solvent until it evaporates, it's there. Then crystal growth from vapor. So in this you evaporate powder and deposit these vapors on seeds. Seeds are necessary as over seeds only it crystallizes. Then single crystals from melt. The procedure is melt polycrystals, or even if it is not polycrystal, you have the amorphous mass also, and then you just melt it and then slowly cool it. Then it will become crystal. But will it be a single crystal? It's not necessary. So many different techniques exist, hence one must think very carefully as which method is the most appropriate for material under consideration for the growth. Now, if we see 80% of the materials are grown using melt growth, nearly 10% using solution growth, 7% vapor growth, and hydrothermal is about 3%. Mostly the quartz crystal, which is grown by hydrothermal growth. You'll see one by one these methods. So single crystal growth from melt. Advantage can grow large size crystals. There is no limit of the size. Usually better control over the nucleation. Usually better control over the shape of final product, good control over growth rates. And what are different issues? The melting points can be very high. Special atmosphere or vacuum needed. Grown crystals may usually have significant stress strain, or constitute evaporation usually occurs. Contamination of crucible material in the grown crystal and may grow different phase from expected. Sometimes, not always. There are few conditions in if you wish to grow a crystal from melt method. First thing is that there should not be any phase transformation from melting point to the room temperature, because if you have grown a crystal, ultimately you will have to use at the room temperature. So if you have grown certain phase, when it comes to the room temperature, it becomes different phase. What are different methods of growing crystals from melt? By melt methods: Czachorski method, Chiropoulos, Bridgman, floating zone, laser heated pedestal growth, micropooling. We will see the Czachorski, Chiropoulos, Bridgman, and floating zone methods in brief. This is Czachorski method, in which you have a container or crucible, and inside you keep your material, and then suppose you have placed the material here and then start heating. These are the heaters. Now what will happen once you have heated and the temperature of this material has gone above the melting point, so it will become, the entire mass will be in the molten state. Now you need to bring a seed of the same material for which this melt is there, and you want to grow the crystal of that, and you bring this slowly and make it in contact of this melt, and then start pulling it while rotating. So the seed is rotating, and then it is moving up. How to find the precise melting point? Because then at this place or this assembly is associated to some weighing device also. So if you have brought this seed into contact of the melt, and the weight of the assembly start falling, that means you can understand that the seed is melting, and therefore it says that melting point is the temperature of the melt is slightly higher than the melting point. And if the melt temperature is lower than the melting point, then immediately you will get a lot of mass attached to the seed, and then you will come to know that actually temperature is low. So by doing this exercise many times, you come to know the exact temperature, and this temperature you keep on controlling using the power supply to this crucible. So once you have found the exact temperature of this melt, which is very, you can say, close to the melting point. In that case, in the ideal situation, the seed will be in the contact of melt, but there will not be any weight change. Then this is in this situation, you start, you can say, slowly start pulling the material or this seed above from this point, and then the crystal will start growing like this. So suppose initially this position was here, now it has come up and this much big crystal has grown in this situation. So in this Czachorowski method, material to be grown is melted in a suitable container, which is called as crucible also. The crystal seed of material to be grown placed in contact with surface of melt. Temperature of the melt held just above the melting point. Just very small difference. It has a high viscosity, lower vapor pressure favors the crystal growth. If the viscosity of the melt is high, these things are favorable, but even if low viscosity material is also there, that can also be grown, but with little difficulties. And vapor pressure should obviously be low, because if vapor pressure is high, your material will evaporate. Then seed gradually pulled out of the melt. Special crystal pulling equipment is used. You don't pull it by hand. Then melt solidify on surface of seed. And melt and seed usually rotated counterclockwise. Sometimes only seed is rotated, and in some sophisticated systems, both melt and seed both are rotated. And they are rotated means if one is rotating in right hand side, another will rotate opposite to that. So, and this rotation actually provide the radial gradient constant. So it actually offset the issues of presence of radial gradient inside the crucible. And because now the temperature gradient is, you can say, taken care, and therefore there will be less defects. Inert atmosphere often under pressure around growing crystals and melt to prevent any material loss, and undesirable reactions like oxidation, if nitrogen is with some materials, it reacts at, and especially at high temperature, it prefers to react. And therefore, sometimes vacuum, sometimes inert atmosphere are used. Another method is there are actually some issues. Suppose you want to grow some material which is having a component like if I give an example of gallium arsenide, the gallium arsenide is having two components. One is gallium, another is arsenic. So at melting point, if you see vapor pressure of arsenic is approximately 10 atmosphere, and the vapor pressure of gallium is only this much. So there is a huge vapor pressure difference. So what will happen? The arsenic will evaporate. If we try to grow this with the Czachorowski method, and you just keep gallium arsenide in molten state, within a few minutes the arsenic will evaporate, and what will left is the only gallium. Therefore, it cannot be grown by a normal Czachorowski method. So for this, you have a slightly modification, which is called as liquid encapsulated Czachorowski method, in which what happens, you just place boron oxide layer over the, you just place the boron oxide with the material. When your gallium arsenide is melt, boron oxide is also will get melt, but it is having a very low density, so it becomes at the top of your gallium arsenide, and protect it, like protect then arsenic from, you can say stop arsenic for evaporation. So a cap is used to encapsulate the melt and it stop evaporation, and this is boron oxide, and the melting point of boron oxide is because 400 degrees centigrade. So when it becomes at 1238, it is obviously be in the molten state, and therefore once you have a melt over that, like you have something water over that, a layer of oil. In a similar way, you have a layer of melt of gallium arsenide over a very thick layer of boron oxide, and then you bring a seed of gallium arsenide which can go deeper inside below the boron oxide layer, and then it touch to the melt surface, and then the process is same. You start rotating it and start pulling it. So these are RF coil used for heating. Because the temperature is nearly 1238 degrees centigrade, which is reasonably high temperature, and in these in such kind of temperatures, radio frequency heating is used. So growing bimetallic, this is just to summarize, growing bimetallic single crystals like gallium arsenide requires a modification of the Czochralski method. Layer of molten inert oxide, this is almost same thing which I have already said. So this actually maintains a precise stoichiometric gallium and arsenic. This Czochralski crystal pulling technique is invaluable for growing many large single crystals as rods to be cut into wafers and polished for various applications like silicon, germanium, lithium niobate, etc. So majority of the crystals are grown using the Czochralski method. Then another melt growth method is Bridgman-Stockberg method. In this method, you have a crucible in this container or crucible. You just place the material whatever you want to grow, and you put inside a furnace. There is one furnace, and this furnace is having a temperature gradient of this kind. Here the temperature is high, here the temperature is low, and so suppose initially initially this entire thing was at this place or even at this place, and then very slowly you start moving this toward this direction. So what will happen? Exactly at this point, whenever it will come here, it is exactly the melting point of this material. And then suppose you have placed a seed, then your material will start solidifying, and because the seed is there, then it will solidify in form of a single crystal over this seed. So a seed can be provided sometimes without seed also, with some kind of some different you can say nucleation can be formed on some different some different kind of components, and if they are not even available, then there will be homogeneous nucleation also. For that, but for that you need to provide a very small area, small volume where the growth start. In that case, this should be of this shape. This method is called as Bridgman-Stockberg method. So Bridgman-Stockberg method is based on a crystal growing from melt. It involves the relative displacement of melt and temperature gradient furnace, fixed gradient, and a moving melt crystal. So gradient is fixed, and this is melt and crystal both are moving. Crystallization of melt starts on the seed as crucible gradually displaced through temperature gradient from hotter to cooler. A controlled solidification of stoichiometric melt of the material to be crystallized in a temperature gradient is achieved. it enables oriented solidification. How it depends on this direction of seed. So if you want to grow a crystal in 111 direction, the growth in 111 direction, in that case you can place a suitable seed which is having a phase of 111 direction, 111 plane. So melt passes through a temperature gradient, crystallization occurs at the cooler end. It is benefit from seed crystals, predetermined orientation and controlled atmosphere. So generally in this horizontal method, a seed is used, but even if you don't use a seed, then also in some cases the crystals are grown. Then next comes is the zone melting crystal growth and purification method, in which it is almost similar to like the previous method. Only thing is that gradient is like this. So suppose the melting point of material is this. In that case, you will make a furnace where the temperature profile will be like this. Here the temperature is constant. Here the temperature is constant, and in between you will have a high temperature, and then you will have a low temperature. So when you start this entire assembly from this place and start slowly moving in this direction. So up to this point, when this portion comes here, up to this point, actually everything will be, so everything will be in the solid form. And then as it starts moving from this side to this side, in that case, this will slowly and gradually, you can say some portion will be in the molten state, and then as it moves, it comes to this place, and then it will start again solidify, and then once you start moving and you make a complete cycle, in that case you will get a full crystal. Now if you want to make or you want to get use of the seed, in that case this crucible position should be starting from actually this place. Otherwise, if you start from here, your seed will also be melted. So only a small region of the charge is melted at one time. Initially, part of this melt is in contact with the seed. Board containing sample is moved at a controlled velocity through the thermal profile furnace zone of material which is melted. As the name of method, it's the oriented solidification also of the crystal, because uh, the the growth direction can be controlled by the seed direction. Partition of impurities occur between the melt and crystals. So there are certain impurities which prefer to stay in liquid or in melt when one solidify, or some impurities they try to move from liquid to the solid. There is a coefficient called segregation coefficient or distribution coefficient, which tells that how much amount of impurity or a particular impurity at interface will go into solid or it will remain into the liquid. So impurity concentration in the melt more than solid phase, where structure energy constant of the liquid side more severe than melt impurity swept out of the crystal by moving the liquid zone. So by this zone is moving. Used of purifying material. This method is used for purification of silicon, tungsten, germanium, especially germanium, gold, platinum, to the ppb level of impurities. Every time every time you start moving one round of the entire zone melting, the impurity, suppose you have certain impurity which goes into liquid more, the distribution coefficient is in such a way. So then after one round of movement, you will get impurities in the impurities will gradually move from this side to this side. And after say suppose 1,000 cycles, you will get all the impurities has come to this level, and this side of the material is very pure. So zone melting is used as the purification also, and for the crystal growth also. Generally, in crystal growth, this method is not very much preferred. However, for purification, this method is always preferred. Then it's a gallium arsenide can be grown by horizontal Bridgman method, and this is what is the you have a furnace. It is like this, and so you have gallium arsenide which is in the molten state here, and then you have placed gallium arsenide seed here, and you have placed lot of arsenic bump. They are solid, and then you have, so what you will do, the it will start the temp where you start raising the temperature, the arsenic actually will start evaporating, and then it will become vapor, and then it comes here, and then your crystal is grown. So the liquid, because the problem was liquid encapsulated growth grown gallium arsenide has a lot of defects, and because of that these cannot be used in many optical applications. So in this see, this crucible is already having gallium arsenide charge. Now what happens, there is a seed is also attached, and then you raise the temperature and bring this entire thing in the form of molten state. Now as we know that the vapor pressure of arsenic is very high, in that case arsenic will try to evaporate, but what we are compensating, we are putting solid arsenic, and that is also heated, so that the vapors of arsenic from this side will also be there, and this entire chamber is closed completely, so nothing goes out. So the vapor pressure of this arsenic vapors will also be there, so it will compensate the evaporation of arsenic. Then that was it was horizontal Bridgman. There is another Bridgman method which is also called as Bridgman-Stockbarker method, in which a crystal is grown by vertically moving downward. So in this you have a crucible. In this crucible you place the material for which you want to grow the crystal, and then entire thing is placed inside a furnace, and the gradient of this temperature gradient of or you say a temperature profile of this furnace is like this. So above this point the temperature is constant, above this point, below this point the temperature is also constant, and only in this small zone, the temperature is actually moving from higher to below the melting point. And then this entire crucible is start from this point and slowly bring it down to this point. So when, just imagine this entire crucible initially was actually here at this point, and then slowly it has moved down to this. So when this point was actually at this particular temperature, at this particular position and temperature, when this point has come at this point, you see the shape of this crucible is made in such a way that a very small volume gets solidified, and this is solidify in when it is in the contact of the crucible, and it can be a random solidification. If you want to provide a seed, in that case you can place a seed here at this point, and then when it comes at this point, the melt start. The melts start to become solidify, and then slowly you bring it down, and then your entire that melt uh, start to become solid at this point. So this is the interface. Now above this it is liquid, and below this it is solid, and if you will bring it down, the entire material will become solidify in form of a single crystal. So you can do sealing also, the crucible for some material which has a difference of vapor pressures. You can use sealing also inside an ampule, or otherwise without sealing also the crystals can be grown. So the crystal growth by passing the ampule through the temperature gradient zone. So that is the advantage of Bridgman technique. Growth stations are less expensive. Sealed ampule permit growth of hygroscopic materials. Temperature gradients are smaller, so the crystals have less thermal stress. And disadvantages: interaction between the growing crystal and the crucible wall, and hence it is difficult to retrieve the crystal. Sometimes, not always. If there is an interaction, if there is, you can say, crystal is sticking to the crucible wall, then it is difficult. There are some materials which doesn't stick; they can be grown easily. And then obviously there is a lesser control over the nucleation, because it is spontaneous nucleation there. If you provide a seed, this can be taken care of. Now next comes the quartz crystal. Uh, First is what is the use of quartz, and why the quartz is important. Its ability for certain non-centrosymmetric crystals like quartz to generate a voltage in response to applied mechanical stress. So suppose you apply some stress, then suppose you have a crystal and you apply a pressure from this side, then you will find that a voltage is actually generated across these two ends. This is called as the piezoelectric effect. And this effect is reversible. If you remove this stress, in that case this voltage will also go. So this is and these are towards certain directions. So compressive stress along 100, this disturbed crystal symmetry, distorting this SiO4 tetrahedra in this crystal. And it creates a charge asymmetry, and therefore a electric charge is developed across the opposite crystal faces, like here and here. And it is in high demand, but it is very difficult to grow, because it has a phase transition from melting point to room temperature. So it cannot be grown by any of the you can say melt methods. So then what are left is vapor methods or solution method. So if you want to grow a crystal by solution method, it need to have at least two conditions. First thing is that you should be able to find out a solvent for this material, and another thing is that the solubility of that should be reversible with temperature, or any other you can say thing which you can control. So it should be having a reversible solubility, and you should be able to find out a solvent. Unfortunately, at room temperature, the quartz is not soluble. So the solubility of quartz in water is very low. So it is actually at 0.38%, even at supercritical temperatures. So this is very low. But still, because there is no other way, so we will have to, there is no other way, we will have to grow the crystal by these uh, uh, these methods only. So one is, now there is another problem. So solubility in water is this much, but the temperature is 374 degrees centigrade. Now, can we raise the temperature of water above 100 degrees centigrade? It will evaporate. So even if it evaporates, but it remains in water phase only, na. So you apply, then you apply more pressure. You with a higher pressure, then you can have more concentration. And there is another thing which we can use is the use of mineralizer. What is mineralizer? It's a complexing agent which actually uh, which solubilized and transport this to the growing crystal. So there are two mineralizers in case of quartz. One is sodium hydroxide, another is sodium carbonate. And at this pressure, if we try to see the reaction, so this SiO2 with this 6OH, it gets converted into this form and you have H2O. If on the other hand, if you have sodium carbonate as used as a mineralizer, the reaction is this, and the pressure is actually the pressure is less as compared to this. So you can choose any of these things depending on the method which you are using. So sodium oxide creates growth rates which are slightly higher, but it requires the pressure, higher pressure also. Now the basic methodologies, you have a water medium. So I'm talking about the hydrothermal growth. So hydrothermal growth is you are having water medium at higher temperature. And the growth is solution growth type. Solution growth is what you prepare a solution and either you reduce the temperature or you evaporate it. Here we can reduce the temperature or we can pass it, pass the vapors to an area where temperature gradient exists. So water function as a solubilizing phase, pressure transmitting agent, often mineralizing agent to the enhanced dissolution, transport of reactants and crystal growth, speed of chemical reactants between solids. Useful technique for the synthesis and crystal growth of phase that are unstable in a high temperature preparation in the absence of water. So this is a very useful techniques where some materials they are actually unstable, but they are present as a so if you say hydrothermal growth, this is a typical setup in which there is a high pressure, high temperature. You have a autoclave here, and then there's a Breffel. The charge of silicon oxide is placed here, and then everything is closed. The temperature is raised. There are several seeds are placed here with this one, and then the temperature is raised. So the water is flowing, and it is taking with the mineralizer, and then this charge, this slowly it goes there, and it goes on the seeds. So the heated mixture, it rises up to the top. One by one, you can see. So the enriched solution of SiO2 is dissolved at high temperature, high pressure. The heated mixture rises up to the top. The heater setup temperature gradient. So there is a temperature gradient inside this part, and the heaters assemblies provide this setup. So the enriched solution come into contact with the seed and it crystallizes. So this enriched solution means the solution containing SiO2, or it comes into contact of seed and it crystallizes. The natural convection by heat and gravity, it is because of the temperature difference, it is moving, and cooled mixture fall back to the bottom and cycle repeated. So the temperature is high, uh, the it goes up and as up and up. When it comes into contact with the seed, some part get crystallized, other part goes here, and then afterwards when it you can say by up to coming this the temperature is reduced, and then through this side it comes back and falls here, and again you have a heater here, which, or heater is actually everywhere, but the temperature is high here. So then again it will get heated and then take more silicon oxide, and then the cycle keep on repeating until the crystal growth is taking place. Here also the same thing has been shown. So you have in this is opposite to that. Here it is SiO2 powder where these are dissolved in the water, and then there is a baffle which allows passes of mineralized species to this side where a seed is placed, and this NOH is at both the places. So it is this water medium where this is placed at 400 degrees centigrade, and seed is placed at 360 degrees centigrade. The pressure of entire thing is nearly 1.7 kilobar, and in this case, in this particular temperature settings, NaOH is used as a mineralizer, and use of silicon single crystal quartz, where the quartz is used in radar applications, sonar applications, piezoelectric transducers, and mass monitors. And the annual global production of quartz crystal is several, you can say, 100 of tons. We see some of the advantage of hydrothermal techniques. These are ability to create crystalline phases which are not stable at melting point, and materials which have a high vapor pressure near their melting points can be grown by hydrothermal methods. It is suitable for the growth of large size good quality crystals with control over their composition, but the growth rate is slow. Then disadvantages: need an expensive autoclaves, and the difficult to observe the crystal as it grows. In case of Czochralski method, or in general other methods, you can see the You can see and monitor the crystal growth. However, in case of hydrothermal growth, generally it is not possible to see the growth of crystal because the crystal is the growth rate are very, very low. Next comes the float zone technique. So this is an alternative method to grow silicon crystals. One method is growing silicon by Czachorowski method. In this method, a polycrystalline rod of ultra pure electronic grade silicon is passed through an RF heating coil. So you have a polycrystalline rod, and then you are passing this polycrystalline rod through a RF heating coil, which creates localized molten zone from which the crystal is grown. So suppose you have this is RF coil. So now there was a solid rod, and from the solid rod you are passing through this coil. So the small portion will be melted, and then as soon as it goes down, you will see a lower temperature, and then it will become solidified. If you have used a seed crystal at one end, then the growth will start on that seed, and then slowly the entire zone, you can say entire rod is passed from one point this point, and then you can see its entire thing has been converted into a crystal. The whole process is carried out in an evacuated chamber or in an inert gas purge. The molten zone also carries the impurities away with it, as in earlier we saw in the earlier method, in which in a horizontal boat we were doing the same thing, and therefore it reduced the impurity concentration. Size of vapor is smaller as compared to the Czachorowski bronze crystal. Now, production of silicon and gallium arsenide wafers. First, what we see, let us see what is wafer. A wafer is a thin slice of semiconducting material such as silicon crystals used in fabrication of integrated circuits and other micro devices. Wafer is the base material for IC manufacturing process. Diameter of a wafer is typically between 1 and 12 inches, and a thickness of nearly about 1 mm. These wafers are obtained by cutting a single crystal ingots into thin slices. So you have a crystal, and then you cut into small pieces. So these are basically crystal slices only. And you can see this is a typical silicon wafer. This is also a silicon wafer, and the crystal. Okay, this I wanted to show just to give you an idea how a silicon crystal or how big a silicon crystal can be grown. So this is a typical crystal grown in a you can say crystal growth factory kind of thing. So this much big crystal, single crystal can be grown by Czachorowski technique at in a single experiment. So now, approximately about 8 to 10 feet long crystal. Now, how the wafer is produced? So first thing is that crystal growth. You grow a crystal like we saw here. Suppose you have grown a crystal now, and then this there are two portions here and here. You cut from these two places, and then you remove these portions, and you will get this kind of crystal. Now after that, in order to you can say mark the direction, you do some flattening. So this kind of flat grinding is done only for like direction identification purpose, and then by using a wafer slice, you can say crystal cutting machine, you slice into small wafers, and then after that you have a edge rounding machine. By this, the edges has been rounded, and then the lapping and polishing is done. Then after that, etching is done, and after that etching, then again polishing to a fine uh, grade is done using the slurry. And then after that, when everything is after polishing, the finally everything is seen. If there are some defects or some if the, say there are some other issues, this can be optically observed. And if everything is fine, then in that case, this wafer is sent for the cell. So this and the crystal growth part. Now let us come to thin film deposition technique. So thin film deposition are basically we can say physical vapor deposition, chemical vapor deposition, epitaxial deposition, electrochemical deposition, and in physical vapor deposition where the vapor is physically transported is are different. Like there are 4 different methods: thermal evaporation, sputtering, electron beam evaporation, molecular beam epitaxy. Then chemical vapor deposition and some epitaxial chemical electrochemical depositions we will quickly see one by one. In physical vapor deposition, the physical vapor deposition techniques are based on the formation of vapor of the material to be deposited as a thin film. The material is in solid form. It is either heated until evaporation or sputtered by ions. Either you can heat it to make it a vapor, or then sputtering is by bombarding, you can sputter out. In the case of sputtering, the ions are generated by plasma discharge, usually of an inert gas. It is also possible to bombard the sample with an ion beam for an external ion source. This allows to vary the energy and intensity of ion reaching the target surface. If the sample is bombarded using electron gun and a focused electron beam, then this is called an electron beam evaporation. So suppose let us see physical vapor deposition. It's a thermal. In the thermal, you have a source. And then you heat, the vapors are formed. If you heat, you vaporize it, and then you have a substrate. Over this substrate, your vapors go from this and get deposited there. So these are purely physical processes. And so these process contains 3 basic steps. One is evaporation from source, that can be done by either thermal evaporation, by electron beam evaporation, by molecular beam, or by laser, or by sputtering. So from the source, you can evaporate by any of these methods. And then the transport of evaporates, these vapors, whatever you have removed from this transport from this to substrate, and then afterwards at substrate these condenses. So like in thermal evaporation, used to deposit thin film on a substrate. Basic vacuum chamber is nearly at 10 to the power minus 6 torque. The mean free path lambda is greater than chamber dimension. The substrate are you place a substrate here which is facing this resistance, where you have actually placed the source which you want to evaporate and deposit. The source of the matter to be evaporated is located below the wafers. The source is heated to the point where it will evaporate. The vapor condenses on the cool substrate and chamber wall. So they can the vapor, they go deposit here also, they deposit in the substrate wall also. Then in electron beam deposition, a filament is heated and then thermal the electrons are emitted. These electrons are by applying a very high potential and then placing inside a magnetic field. These are allowed to fall on the substrate, and then they heat the substrate, and then they remove the substrates from sorry, not substrate, this source, and from the source they remove this material, and then this material is physically, or you can say it is, this material goes and deposit on the substrate. In the sputtering, you have a atoms that are see these atoms are ejected from the solid target material due to bombardment of the energetic particles. It is basically the momentum exchange between the ions and atoms in the material due to collision. So you have some atom or ions which is having a very high kinetic energy. This comes and strike with these atoms, and some of the atoms are removed from the surface, and these atoms then this goes and get deposited on the surface of the substrate. So for sputtering of a working gas such as argon is required. Now this is a by sketch we can understand. So suppose we have a substrate where we want to deposit some material, and this whatever you want to deposit, it is in the form of a target. Then a can say a plasma of argon or some other gases, mostly argon only, is generated. So you have ions, positive ions, and then you apply a high voltage. So with that, this suppose you apply minus negative voltage, a very high negative voltage, what will happen? These positive ions will go and strike on this target and sputter out some atoms from this target. These sputtered out atoms will move, and they will move in all the directions, but they can go in on the substrate also, and then they will deposit on the substrate. So there is one problem in this. So since these atoms will go and actually they strike, these are ions, positive ions, they will go and strike, so they can get accumulated. So there can be a problem after certain time. The sputtering process may stop, because then actually this target surface will be covered by these ions. So to avoid that, the RF sputtering is preferred in such cases in place of DC sputtering. So in DC sputtering, it's only fixed voltage which is applied, negative fixed voltage. If you see with the pressure, if you put the argon pressure, if the pressure is increasing, if you increase the pressure up to a level, the sputtering increases, sputtering yield or deposition rate, it increases, and after that to a certain pressure it remains almost in the constant zone, and then start reducing. So as I said, DC sputtering has some issues, and therefore to avoid those issues, RF sputtering is preferred. It avoids charge buildup by alternating potential. So means one cycle you will have target which is positive and substrate negative. In the other half cycle, this will be, the polarity will be opposite. However, so by this, the accumulation of charges or ions at either substrate or targets can be avoided. We can use higher frequencies also in the RF sputtering, and we can use lower sputtering, means lower frequencies also. So if we use frequencies less than about 50 Hertz, in that case, electrons and ions in plasma are mobile. Both follow switching of the anode and cathode, basically DC sputtering of both the surfaces. And if we use frequencies above 50 kilohertz, the ions can be no longer follow the switching and electrons can neutralize positive charge buildup. So then we comes to chemical vapor deposition. Chemical vapor deposition is a process where material is deposited from a vapor by a chemical reaction occurring on or in the vicinity of normally heated substrate surface. The solid material is obtained as a coating, a powder, or as a single crystal. By varying the experimental conditions, substrate material, substrate temperature, composition of the reactant, reaction gas mixture, total pressure gas flow, etc., material with different properties can be grown. In a typical CVD process, the substrate is exposed to one or more volatile precursors which reacts and decomposes on the substrate surface to produce the desired deposit. During this process, volatile byproducts are also produced. So some of the products which are actually volatile, these can be removed from this side also. So this is a typical CVD process in which the source materials are passed from this side. Then you have substrates placed here. There is a heater. So these all these you can say reactants, they go here at high temperature at the near they get the reaction takes place, and the compound which has been formed due to this reaction, this deposited on these surfaces. So like suppose you have like three different compound, you can input from three and then purge gases. This is just to remove the byproducts, and these three processes gases they move to this chamber, and then at this place where the temperature is high, they react to each other, form a new compound, and that new compound is deposited on the substrate here. Then next comes the epitaxy. So what is the meaning of epitaxy? Is actually epi means above and taxis means in ordered manner. So this is basically a layer by layer growth where one layer over the other layer is grown. So it is deposition of crystalline layer on a crystalline substrate such that there exists a well-defined relationship between the crystallographic orientation of layer and the substrate. Suppose you want to deposit uh, one layer over the other layer in the crystalline form only. So it is a very crucial technology for semiconductor thin film technology, because the size of devices, or you can say thickness of these are very critical, and there should not any actually there should not be any large mismatch in the lattice parameters, and no chemical reaction. There should not be any reaction between one layer or another layer, and there should not be any thermal mismatch also. So epitaxies are of two types. One is homoepitaxy, another is heteroepitaxy. In homoepitaxy, the substrate and epi layer are of same, like you are depositing silicon layer over the silicon substrates only. So and like gallium arsenide layer over the gallium arsenide surface or any other layer. So epitaxial layers are these are purer than the substrate. These homoepitaxially grown layers. Low growth temperatures. Layer can be doped independently of the substrate, and they can be deposited uniformly also. Then another is heteroepitaxy, where one type of layer is grown over the other type of layer. Suppose you have a substrate, the lattice parameter of the substrate, or you can say the substrate, the chemical composition is different. So the sapphire substrate, suppose you have a sapphire substrate and growing gallium nitride epi layer over it. Similarly, on silicon substrate, suppose you want to deposit a single or a thin layer of gallium arsenide. This kind of epitaxial growth is called as heteroepitaxy. So in this, like this, by use of heteroepitaxy, it's possible to have band gap engineering. Quantum wires, and quantum dots are actually deposited by this method, because these very small layers behave like quantum dots. Then next comes the liquid phase epitaxy, in which what happens, the reactants are dissolved in a molten solvent. So you have a solvent here, and it is in the molten state, and temperature is high, and then you have a substrate which is placed here. So what happens, this board now this is in tilted state. You make it straight, just okay, you tilt it and you bring in this way. Now your solvent, uh, this molten solvent has come into contact with the substrate. Now after some time, the time can be optimized, and then you bring it back again to this situation. So now you will have a thin layer of the the material which you are having, you want to deposit over here. This can be by see, this is one method. This method is called as tipping mode, in which actually you are just you can say putting it like this way. And there is a dipping method, in which the solution, source solution, is placed inside a crucible, and the substrate is placed over some arrangement, and then this is brought here, and it is just touched with the solution. So you can say this solution, and then kept there for some time, and then slowly it is removed. And then there is a third mode, which is sliding mode, in which suppose you have a substrate, and then you place a solvent here, like this here, and then slowly you just move this thing, this part you keep on sliding from this way to this way, and in both directions. So every time it comes under contact of this solvent, you get one layer deposited, and then it's like this. So you have a gap here. So with this, now it is contacting with this solvent. This solution, actually not solvent, this solution. Now it will go back, and then you keep on moving this both the sides, and then every time you get a layer deposited over that. So what are advantage of liquid phase epitaxy? It provides high quality layers, it is fast, it is inexpensive, and incongruent melting problem can be tackled because you are not actually melting the material, but providing a solution. So only you need to find a proper solvent, and epitaxial films have better compositional uniformity as compared to the bulk rule crystal. But then you can say thickness is small. Suppose in a bulk, if you say crystals are large, you cannot grow you can say you cannot make a 3D structure using films for a very long order. You can grow maximum few nanometer or few micron up to with such a high crystalline quality. If you want to go in, you can say in centimeters, then bulk grown crystals are better one. Then third comes vapor phase epitaxy. It's similar to, it looks similar to what we saw chemical vapor deposition. So suppose, but there are some differences here. So you have three sources. So it is, as I said, it looks like CVD. It is actually a specific type of chemical vapor deposition that use metal organic sources gas. So you have some metal organic sources gases, and then reactants. These reactants are introduced as gases in this chamber, and material to be deposited bounds to ligands. And then ligands dissociates and allowing desired chemistry at the surface. So suppose you have a metal organic compound here, and then this is arsenic, this gas, and arsine. This gas is transported here, and if we keep this reactor at high temperature, in that case at the substrate, suppose the substrate is near to this temperature, then a reaction takes place and gallium arsenide is formed on the substrate, and this is also forms methane, which can be actually swept away by the different gas. Another example of vapor phase epitaxy for deposition of silicon. Silicon can also be deposited by this. So for this, uh, uh, silicon chloride and this is allowed to react with the hydrogen, and you get silicon, and so in that case the silicon chloride is actually inserted with hydrogen, and then you can deposit silicon small layers. So for this requirement is the precursors must be sufficiently volatile to allow acceptable growth rates, and it should be heated to a desired temperature, and at that temperature pyrolysis should take place, and the less hazardous chemical should be preferred. The next one comes is the molecular beam epitaxy. This is also like you have sources, you have different effusion cells, and from this you keep the compounds here, and you increase the temperature, and then there are shutters. So then whatever you want to deposit, you can remove the shutter, and then the temperature is increased, and this entire chamber is under a very high vacuum, and the substrate is you can have a provision of rotation also, and then you open the shutter, and if the temperature is you can say high, the temperature is increased, in that case it will be like a thermal evaporation only, but with a very you can say controlled rate. So suppose you want to deposit gallium arsenide, so this gallium arsenic, and so these will be opened, and then it will be deposited here, and then for dopant also it will be different. So but the disadvantage is they have very slow growth rates, approximately 1 micron per hour, and very low pressure, about 10 to the minus 18 torr. But complex compounds like HTSC, biocompatible ceramics, etc. Can be grown, but the system is very expensive actually. So because the beams are actually of a very you can say the beam can be controlled up to a molecular level so precisely, and therefore this is called as the molecular beam epitaxy. This is typical, just a like in a simple picture. So you have different efficiencies here, different compounds you have placed. This is under very high vacuum, and you have a substrate here, and which is rotating also. It's optional, and then a wafer is here, and then see you can deposit whatever you want to deposit with. So it is a kind of thermal evaporation only. It is kept at very you can say high vacuum. It is advantage of very low background and high mobility. Compound can be deposited. The abrupt interfaces can also be deposited. There is a very good thickness control, and there are independent temperature controls for each of these cells, and you can switch the metals easily, and it's a low temperature growth because and then you have a in situ control. Now we'll come to the last part, which is 2D and 3D printing. So if we see a domestic printer deposits substance on substrate paper, which is a normal 2D printer, what it prints a predefined text or picture, and how it prints, it calculates that on the piece of paper at what distance it need to place the ink. It has a precise XY stepper motor movement. These stepper motor place the printing head at exact position, and then ink is evaporated from the printing head on the paper. So suppose you have a so this kind of scanner. So you have two stepper motors. One is here, another is here, and then you move the head using both these reasons, and you bring the head at, suppose you want to print at this particular point, then by using these two stepper motors you bring the head here, and then evaporate the ink, then evaporate the ink at this particular point, and this is called as 2D printing. So 2D printing, or simply printing, is the process of putting an image on the paper, because then it can go anywhere on this paper using this XY control, and at that particular point it can deposit the ink or evaporate the ink. Now if we extend the control of third dimension also, suppose here also, if we you can say add another movement like moving in this direction, and then in place of because ink anyway there is no point in putting ink over ink, and then put some material in place of ink, then it can be called as a 3D printer. So it is like that. You have one direction, two direction, and this is also third direction for the printing. So if appropriate deposition substance is selected, then one can fabricate 3D shapes also by layer deposition by moving the printing head in Z direction. This is a revolutionary concept which is changing the manufacturing process for many items. Thus, 3D printing is an additive process where layers of materials are built to create 3D part. It is opposite to subtractive manufacturing process where a final design is cut from a larger block of material. Like making metal parts, thus a 3D printing creates less material wastage. So actually it is additive printing. Whatever, suppose we want, what is subtractive printing? Suppose you have a block and you want to make some small rod out of it. So you will cut out and you can say remove the other part. That kind of processes are called as subtractive processes. So there are variety of 3D printing materials. For example, thermoplastics, resins, metals, powders, and ceramics. These are placed in place of like just like in normal printer. If you can fill it with thermoplastics, some resins, or some metal powders, and some ceramics, then you can layer by layer. Suppose you want to actually deposit metal, or you want to make a brick of metal of this kind. So why in a similar way you can as we were doing 2D printing, you move at this point precisely via software, and then deposit one layer of some metal, then again come back, again deposit, and slowly start moving in the and start moving in the third direction also. There are three broad types of 3D printing technologies, that is sintering, melting, and stereolithography. Sintering is a technology where materials are heated. Okay. Where the materials are heated but not to the point of melting. So material is heated but it is not reached up to melting stage. The metal powder used for direct metal laser sintering, while thermoplastics powders are used for selective laser sintering. Melting methods of 3D printing includes melting of substance prior to placing on a substrate. So in sintering, it is not more the temperature, though it's higher, but it is not in the molten state. However, in melting methods, the material is first uh, melted and then it is deposited. In stereolithography, photopolymerization is used to create parts. Here, appropriate light wavelength is selected to interact with the material to selectively cure and solidify the exposed part. So here, you actually use light to photopolymerize wherever you want to solidify. So the 3D printing has been categorized into various groups, mainly seven, by additive manufacturing, general principles, terminology. All forms of 3D printing fall into one of the following types. What are those? Is a binder jetting, direct energy deposition, material extrusion, material jetting, powder bed fusion, sheet lamination, wet polymerization. So I think 3D printing industries has a lot of scope in automotive, aerospace, medical robotics, etc. for making precise parts. So these are few 3D printers where uh, you see some object is being printed, this kind of thing, and this is subject. I think we should stop here. If you have any question, I can answer. Okay, if there is no question, then thank you very much. वो तो भेज ही दूंगा ना।